Let's talk about residues in the wild, because there's a lot of theory that you can see about residues and read about, but it's actually kind of a natural and simple process with a big surprise at the end because of how the residue process brings to light properties of functions, of real functions that would otherwise be invisible. It's like having another, you know, dimension, as you see in string theory, where we don't live in a four-dimensional universe. We live in a 10-dimensional universe where six of them are really small and we can't see them and stuff goes on there. This is what happens with using residues. So first, residues in the wild. If you look, there's limits and there's this and there's it's not that bad, because what happens is if you take a meromorphic function with a pole, and let's put the pole at some point A is a complex number, then what you can do is expand it, and this is often how it comes to you. So I'm writing out part of the expansion. So we start with this. This is the polar part of the expansion, where we've got z minus a would be 0 if we actually did it, and it's on the bottom, so that's how I got this scar in 8th grade. But these are the negative powers of z minus a that appear. And then you get a constant, and then you start in with the positive powers that start to look like a Taylor series. So this is a Laurent series, and it's a theorem. It's the Laurent theorem that complex meromorphic functions can be written this way. So the problem is, when you integrate this, then what you have is that almost all of these integrals around a closed contour in a simply connected region, the things that you see in the statement of the residue theorem, all of these terms have antiderivatives except for this one. And that means that this is what is going to be happening in the residue theorem. I've got a note to myself here that says, look on page 49 of Alfor's. I think that means 149. So the residue, we'll check this out later, is just a to the minus 1. Because by Cauchy's theorem, all of these other things have antiderivatives, and so they integrate to 0 over simple closed paths around simply connected regions. So, and the residue theorem now just says, well, once we have these residues, then, and this is, I think, theorem 17 in Alfor's, it says if you have, under the usual circumstances, you've got some region omega and a simply closed curve in omega. It actually doesn't have to be simply closed. So we've got gamma, a curve in a region omega. And inside of gamma, this is the deep Jordan curve theorem that says there's an inside and outside. So inside of gamma, we've got some poles, and the residue theorem says that the integral over gamma of f of z dz, those are poles of f, and this is something that's actually easier to say in words. It's 2 pi I times the sum of the residues but they have a multiplicity. If there's a winding number, then you have to take the winding number into account. So the precise statement is in Alfor's, but it's like, the sum of the residues. It's just the sum of the residues. So so there you go. So we've got the winding number as a multiplicity for each of these. Okay. There's a very striking application of this, which is the argument principle, which I just want to mention briefly, which is actually something I use quite a lot. It says that 1 over 2 pi I. Ooh, I forgot the 1 over 2 pi I in the previous. No, I didn't. Never mind. 1 over 2 pi I, integral over gamma, same considerations about what gamma might be of, now not f, but we're going to take the logarithmic derivative. So that's a fraction. Top is f prime of z, bottom is f of z, dz. Well, when you look at the logarithm of something that has a bunch of zeros and poles, when you take f prime over f, what you get is a series that kind of looks like this around each of those poles, and you get residues. But the residues are only plus or minus 1, plus 1 and a 0, minus 1 for a pole. So it's the poles minus the zeros. Oh, I got that backwards. Sorry, it's the zeros minus the poles. So again, the precise statement is in L4s, but it's zeros minus poles. And so these things work out really quite well. So that's the argument principle. Okay, so this, if you start to get into algebraic geometry, the generalizations of the argument principle come up as a very, very important tool, and we want to know about the zeros minus the poles, and we might see some of that later in the semester. But there's another way to handle this, which is, I just think it's a lot of fun to do this, which is to look at definite integrals and see what, these are real integrals, definite real integrals, and see what the residue theorem says about them. Now, your first reaction should appropriately be, what? We're talking about poles for meromorphic functions that are probably happening someplace in the complex plane, and then we're going to do definite integrals along the real line. And so let me show you what's going on here. And I'm going to focus on an example, and the reason I want to focus on this example is that it really does have all of the essential elements of what goes into working with these integrals of rational functions. L4 says definite integrals, but that just means integral. Anyway, you're going to integrate rational functions along the real line, but what you're going to see is, because of the poles, the integrals get are doable in terms of residues. So the first thing is that this example contains all of the essential elements of the method here, and the second one is this example I'm about to do is one that you can do just using ordinary calculus, and so we can compare what we get from calculus with what we get from using the residue theorem, and of course they come out to be the same. So let's change colors here, and what we're going to look at is the integral from minus infinity to infinity, so that's over the whole real line, of the following. It's a fraction. The top is just dx, and the bottom is x squared plus 1. So this, let me point out a couple of features of this integral. It's over the whole real line. The degree of the bottom is 2 more than the degree of the top. That's very important for doing these. There is some stuff about when the degree only differs by 1, but you have to use a different technique. So we have the degree on the bottom is 2 more than the difference of the top. I'm sorry, than the degree of the top. And we have a rational function, and we would like to integrate it. Now, we've taken calculus, so we know that the antiderivative of 1 over x squared plus 1 is arctangent of x. So we could actually do this. But let's do it with residues and compare. Okay, so here's the deal. So what you need to do is expand out this rational function that's inside the integral, and use partial fractions to do that. And I've taken the liberty of doing that in advance so that we don't have to watch a lot of me doing algebra. And the partial fractions decomposition that I get is this. I'm going to write it down and then I'm going to show it to you. And there it is. So the roots of x squared plus 1, it factors, it's a fundamental theorem of algebra. It factors over the complex numbers into 2 linear factors, x minus I and x plus I. and the partial fractions decomposition, you get some i's to play around with, but there it is. And so this function has two poles. Now, when you look at it from the real perspective, you go, what? There aren't any poles? X squared plus 1 is never 0? Well, it's never 0 in the real line, but it is 0 in the complex numbers. And of course, everything has a 0 in the complex numbers. That's the fundamental theorem of algebra. And so we're going to look at these poles. Well, actually, we only need to look at one of them. So here's the standard technique. The standard technique is to say, I'm going to integrate from, I never gave these names. Okay, well, I'll just say over the following path in the complex plane. So L4 uses rho, so I'm going to use rho. So let me show you what we've got here. So the path is the minus rho to rho. Of course, that's the real part. So you've got this segment along the real line, and then you've got this semicircle. And the semicircle has radius rho as well. So let me indicate what the orientation is, although that should not be a surprise. So there's the path that we're going to integrate over. Simple closed path satisfies all the hypotheses of the residue theorem or of Cauchy's theorem or of Cauchy's integral formula or all of these things. It's got the right kind of path. And the residue theorem says the integral over this path of, now let's call it z, dz over z squared plus 1, is the sum of the residues inside the path. Well, as long as rho is bigger than 1, there is only one pole inside this region. There's only one pole inside this region. So instead of now looking at an integral as taking account of every single real number, we're just going to see what happens at one point. So the pole is at I, so I've drawn it in, and the residue, well, we can get the residue right here. This is what I mean by residues in the wild. These can be easy to get sometimes. The residue is 1 over 2I. So the integral over this path, which I'm going to indicate symbolically, of dz over z squared plus 1 is, I think we do need a drum roll for this, it's 1 over 2I. I'm sorry, 1 over 2 pi I times that integral. So this is just standard residue theorem stuff, 1 over 2 pi I integral. Well, it's the sum of the residues inside. There it is. There's one residue inside. The other way of looking at this is to say the integral over that path that we've just defined of dz over z squared plus 1 is, I'm going to do some arithmetic in my head, excuse me, pi. I just did the 1 over 2 pi I from the other side. So as far as doing this integral by residues, we've got a pretty easy situation. You don't actually have to integrate anything. You don't actually have to integrate anything to find out that this integral is I. I guess that's just an alternative way of integrating or something. It's not related to the fundamental theorem of calculus or anything like that. So, well, it is deep down because Cauchy's theorem is related to the fundamental theorem of calculus in deep ways. The problem is, what we came in asking about was the integral over this piece of the curve that describes the region, the part that's along the real line. But we've also integrated over this semicircle, and this is where things get fun. Basically, the integral over the semicircle, this is real loosey-goosey. You can make this more precise, but in fact it works out quite nicely. The integral over the semicircle part is, I'm going to say it's like, I'm going to estimate it. And what I'm going to say is when rho, the radius, is really big, the z squared plus 1 part isn't going to make much difference. Rho squared plus 1 when rho is 1,000,000 is still rho squared. And so that part's really big. So I'm not going to say it's equal to, but I'm going to say that it's like, well, it's like integrating 1 over rho squared over that semicircle. So what we're going to have is the value of the function times the length of the path. So this is a standard way of estimating integrals. This happens a lot in doing integrals by residues. So you take the length of the path and some, say, maximum value or something of the function, which is basically what we have here. And so the path is a semicircle. So instead of being 2 pi rho, it's pi rho. It's only half the circle. And that is like 1 over rho. Excuse me, sorry. So what basically this integral is like 1 over rho. So when rho goes to infinity, that means that the integral over the semicircular part goes to 0. So that goes to 0. That's why you had to have the degree 2 less on the bottom, because what you have is the length of the path is 2 pi rho. That's like, and then the take the top and the bottom and cancel them all out and do the limit things, and you find, I mean, it would be the same thing as trying to find the limit there. You'd pull out the common factors and you'd find out you've got 2 pi rho times 1 over rho squared. Piece of cake. Okay. So what that means is that the integral of dx over x squared plus 1 over this part of the line, the circle doesn't add anything to that integral. So we did that integral using residues, and the circle contributed 0, which means that everything that's left is contributed by that portion of the real line. And so the integral of dx over x squared plus 1 over the whole real line is pi. So we can take that home and have it for dinner. If you go back and do the calculus techniques for integrating that same integral, you have to do it as an improper integral. So let me just kind of outline it here. So first of all, because of the symmetry, this is 2 times the integral from 0 to infinity of dx over x squared plus 1, which is 2 times the limit as, say, capital T goes to infinity of the integral from 0 to t of dx over x squared plus 1. Let me show you what I've been writing here. So this is now the real analysis or calculus way of doing it. So we take advantage of the symmetry, and then we have to do the improper integral, which means we're going to take the limit as we go, as t goes to infinity. And that's just arctangent of t. So what angle has tangent infinity? Pi over 2. So we do get the same result. The thing is, the residue thing can be a lot easier for more complicated rational functions than this, but this should give you some confidence that this technique really works. And the key is that the integral over the semicircle part goes to 0, so what you're left with is the integral over the real part, and that's just the sum of the residues.